Hello, I'm Jiping from Tsinghua University, and I'm here to present our work, GraphAce Secure Two-Party Graph Analysis, Achieving Communication Efficiency. This is a joint work with Chen, Yunyi Chen, Xiaoyu Fan, Xiaowei Zhu, Chen, and Wenguang Chen from Tsinghua University and Ant Research. First, let me introduce the background about this work. First, let me introduce graph analysis. This refers to iterative workloads on a static graph. Within the graph analysis process, the graph topology is assumed to be immutable, while the vertex attributes can be mutable across iterations. Here is an example of a financial graph. In the financial graph, each bank account or card is a vertex, and each transaction is an edge. Assuming that if card 0A was marked high risk before, then we should increase the risk of card 1B via 3 hops from card 0C to card 1A. So that after 3 iterations of graph analysis, the risk of card 1B should be increased. However, in reality, graph data often arise from different entities. In the financial example, the full graph is shown as above, but each bank only knows a subgraph. For example, the bank 0 only knows the subgraph on the left side, and bank 1 only knows the subgraph of the right side. If we could analyze the full graph, we will achieve better results than individual analysis. For example, if the banks operate individually, bank 1 cannot raise the risk of card 1B because it does not have any knowledge about the left side. So this information could not be propagated to the right side. However, subgraphs cannot be directly exchanged in many cases. For example, each party may consider the subgraph valuable, or laws or regulations may prohibit transferring sensitive data, such as transactional records. So we need secure graph analysis. It should achieve the correctness so that each party learns the analysis results of its vertices, and the security, which means that each party should learn nothing beyond the above results, especially about the other party's graph or any intermediate values. Next, we introduce the related work. The first related work is GraphAce. It's published 10 years ago and is the first secure analysis framework with subquadratic complexity. It used Bytonic sorting and scanning to convert graph analysis workloads into circuits, and they used Gabor circuits so that it can be evaluated securely under 2 parties. Because it's sorting, it results in the log squared factor. The next related work is Araki's work. Their solution is mostly based on GraphAce, but they optimize the sorting into 3-party permutation protocol based on secret sharing, so that the bottleneck is not the sorting anymore, but the parallel scanning process needs an additional log factor. They also assume the honest majority that no 2 parties collude, so that it's actually a 3-party honest majority setting. Another related work is Graphity. It's concurrent with our work. It adopts a communication-free prefix sum over secret sharing, so that they get rid of parallel scanning with a log factor, only needs a secure permutation, which is linear complexity. However, they still assumes an honest majority, so that they work on 2 parties with 1 helper and a non-colluding assumption. Also, we find a difference that previous studies are not end-to-end frameworks. they assume that the graph is already garbled or secretly shared among 2 or 3 parties, and they did not discuss the conversion from the local subgraphs to the garbled full graph, or how to distribute the results to the parties. So our question is that for secure two-party graph analysis, can we support end-to-end analysis without requiring any additional non-colluding party and use even less communication? And our answer is certainly yes. Our GraphAce can support end-to-end analysis and without additional non-colluding party, and we can completely eliminate any communication about the number of edges E. So how can we achieve this? Now we will introduce the design of our GraphAce. To start, let's look at the problem formulation. In our setting, each party B inputs a vertex set and an edge set, including their weights. Our public information is the specification of the graph analysis application under gather apply scatter model, and the approximate scale of the number of vertices of the 2 parties is CL log 2, the number of vertices. Our security assumption is that we can achieve the simulation-based security against semi-honest parties, so that the party learns nothing beyond the final analysis results, especially nothing about the other parties' inputs or any intermediate results. So here is our insights. We have observed that insecure two-party graph analysis is equivalent to distributed plaintext graph analysis over 2 machines. However, as far as we know, almost all distributed plaintext systems do not require per-iteration communication about the edges E. This inspires us to resetting to plaintext solutions and then successively addressing its security concerns and try not to introduce any communication about the edges. After this, we can obtain a secure two-party solution without any communication with edges. So let's look back to insecure two-party graph analysis with an example algorithm where each vertices sums the weights from incoming edges from the previous iteration. For example, for vertex y, the weights should be r plus c plus j of the previous iteration. We can implement this insecure analysis with 2 steps. The first is the local steps, where party 0 computes r plus c, while party 1 only picks the weight of j of previous iteration. And the cross-party steps is to interchange the values and sum up, so that both parties get the new weights for the vertex y, so they are ready for the next iterations. This results in a constant number of communication for each vertex, which is independent of the vertex degree, only need to send the local sum. So that for all vertices, we only need to OV per iteration communication. We find that there are 2 security problems of this insecure method. The first is about weight privacy, because any intermediate values are sent in plaintext, and obliviousness, which means that if we send the local sum of our vertices, we would let the other parties know the vertex set, because the other party knows which vertices are sent. So the next part is how to solve these 2 security problems with security primitives. The first is protecting the weights with mixed primitives. We use a mix of homomorphic encryption and secret sharing. The homomorphic encryption is used for local computation. We use XHB to denote a value X encrypted by the other party 1 minus b's private key and stored in party B. This ensures that no party can directly decrypt the underlying value. And the secret sharing enables cross-party conversions so that the cross-party interchange part can happen. In this example, the secret sharing enables the cross-party conversion from the homomorphic ciphertext from one party side to the other party. So the local and cross-party steps now operate on the ciphertext rather than plaintext. And we should highlight that the mix is necessary. If we only use secret sharing, we would introduce per-edge communication because SS cannot operate locally. If we only use homomorphic encryption, the corporate part cannot happen. So this solves weight privacy, which achieves OV communication per iteration, but we still need to address obliviousness. To achieve obliviousness, we design a novel data structure named chaos table. We assign a random unique position for each vertex, so that the vertex in the intersection set has the same position as received by each party. For example, the Y is received as position 2 and 2 for both sides. The method to assign this position will be introduced later. After this, the all operation reference the vertices by positions instead of by name. And the cross-party step works exhaustively for all possible positions so that the actual vertex set is hidden. This results OV communication per iteration as long as the range of the positions is still OV. So how to assign this position? We build a secure two-party protocol so that each party prepares the arrays and add some paddings. And we use secure protocols to merge two sorted arrays and generate a random array so that the merge is reverted for this random array. After the revert, we review USENIX elements of each resulting array to the party B. And everything is secured with secret sharing based protocols so that the party learns the revealed positions but nothing else. We can prove that this protocol satisfies the previously required chronix and randomness, and the result is 0 in a linear range. And this protocol is efficient because it only needs OV time to build. And here is the full workflow of our system, which generates the previous example algorithm. It consists of six steps, and 4 and 5 steps are repeated for each iterations. And you can refer to our paper to more details. And for the security, we can prove that any message sent over the network is either ciphertext or independent random numbers from non-distribution, so that we can prove that with a simulation-based method that our system GraphAce is secure against static semi-honest adversaries. Okay, finally, we can look at our experimental results. We mainly compare with GraphAce because it is the only existing two-party solution without an additional non-colluding helper. And we use 5 graphs of different scales from hundreds of vertices to 100 million of edges. We use 5 different applications. The first 3 applications can be implemented by GraphAce with partially homomorphic encryption, while the 2 two-letter applications should be implemented with FHE, and we use 40 cores per party for CPU and 3 simulated network settings. The first part is about the communication efficiency. We can see that the GraphAce can have a better saving ratio, giving a larger graphs, because we offer better complexity. We are linear, while the GraphAce needs additional log factors, and we can save hundreds or even tens of thousands times of communication. For the first 3 applications, we can achieve more than 10,000 of communication saving. And for the 2 applications we have used FHE, we can still achieve hundreds of communication saving. For speed up, it's similar that we can achieve better speed up on larger graphs. And if the network is more demanding, we can achieve even better speed up from over 1,000 times to over 10,000 times. This data point is the page ramp algorithm, and assuming an intercontinental network for the largest graph, and the GraphAce would require over 4.5 years, and we only need 2.1 hours. Similarly, if the application could use PHE, is the first 3 applications, then we can get better speed up than the 2-letter applications that should use FHE. And we tested on 5 graphs with the same number of V plus E, but different the ratio of E and V, so that we for the communication, we can consistently save communication against GraphAce, and and for time it shows a similar ratio, so that our framework GraphAce can outperform GraphAce for most of the cases. We have submitted our artifacts to the denote, and we have earned all 3 badges. And you can see our artifacts appendix for further information. And that's all for my talk, and thank you for listening.